It is rare to see a skyscraper that looks like it is standing on stilts, hovering over a city block with a lightness that defies the millions of pounds of steel and concrete above it. When you look at the Manhattan skyline, specifically at 601 Lexington Avenue, you see a building that should not, by traditional rules, be there. It sits on 4 massive columns, each 9 stories tall, but they aren't at the corners. Instead, they are positioned in the center of each face. This design was born out of a specific constraint, the presence of St. Peter's Lutheran Church on the corner of the lot. The engineers couldn't move the church, so they decided to build over it. This required a radical approach to how a building manages its own weight and, more importantly, how it resists the invisible, relentless force of the wind. To make this work, the lead engineer, William Lemessurier, utilized a system of Chevron bracing. These are inverted V-shaped steel frames that funnel the massive loads from the upper floors down through the building's skeleton and into those 4 central columns. This was a masterclass in structural efficiency, or at least it seemed to be until a series of small, seemingly insignificant decisions began to stack up. In engineering, every choice is a trade-off. You trade weight for stiffness, complexity for cost, and innovation for familiarity. The Chevron bracing was designed to be welded. Welding creates a continuous, rigid connection that essentially turns the steel members into a single, unified piece of metal. However, during the construction phase in the mid-1970s, a change was proposed. To save time and labor costs, the contractor suggested using bolted joints instead of welds. At the time, this was a common substitution. Bolts are easier to install in the field and require less specialized labor than high-quality structural welding. The change was approved, and the building was completed. But the math behind that approval relied on a traditional understanding of wind loads that didn't fully account for the unique geometry of the Citicorp Center. Most buildings are designed to withstand winds hitting them head-on, perpendicular to their faces. In a standard corner column building, this is often the most critical case. But for a building on central stilts, the evidence points toward a different vulnerability: quartering winds. These are winds that hit the building at a 45-degree angle, striking the corners instead of the flat surfaces. When wind hits a building this way, it creates a complex set of pressures that can actually increase the load on the bracing system by 40%. The original calculations for the bolted joints had not fully accounted for this increase. The missing angle in the design process wasn't just the wind direction, it was the behavior of the joints themselves. A bolted joint, while strong, behaves differently under tension and shear than a fused, welded joint. When Diane Hartley, an engineering student at Princeton, began looking into the building's design for her thesis, she noticed something the professional engineers had overlooked. She reached out to the firm with questions about the building's stability in these diagonal winds. When Lemessurier went back to his calculations, he realized the student was right. The combination of the bolted joints and the quartering wind loads had significantly reduced the building's safety factor. Under certain conditions, the stress on those bolts could exceed their capacity, leading to a failure of the bracing system tier by tier. This wasn't a hypothetical risk. The hurricane season was approaching. The mechanism of the issue was a mismatch between the theoretical model and the physical reality of the constructed joints. The system pressure was mounting, both literally from the atmosphere and figuratively within the engineering firm. They had a building that was occupied and functional, but its skeleton had a hidden flaw. What followed was one of the most remarkable, and for a long time, secret repair operations in engineering history. They couldn't just evacuate the building without causing mass concern, so they worked at night. Welders moved tier by tier through the building, welding 2-inch thick steel plates over the bolted joints to restore the structural integrity that the original design had intended. Throughout this process, they also relied on a relatively new piece of technology, the tuned mass damper. This is a 400-ton block of concrete located near the top of the building, floating on a thin film of oil. Its job is to move in opposition to the building's sway, acting as a counterweight to dampen the vibrations caused by the wind. While the damper helped reduce the load on the structure, the engineers knew it wasn't enough to compensate for the bolted joints. The lesson of the Citicorp Center is one of professional responsibility and the danger of the standard substitution. It highlights how a minor change in a component, like switching a weld for a bolt, can have systemic consequences when the overall design is non-traditional. It also serves as a reminder that the most critical flaws are often found at the boundaries of our assumptions. We assume that because a method works for 99% of structures, it will work for the 100th. but engineering is defined by the exceptions. The evidence boundary here was the quartering wind, a factor that was known but not prioritized because it rarely dictates the design of more conventional buildings. By acknowledging the error and fixing it in silence, the engineers protected the public, though the story didn't become widely known for nearly 20 years. It forces us to ask, where else in our built environment have we traded structural redundancy for economic efficiency? Every time we walk through a city, we are trusting that the trade-offs made by the designers were the right ones. If you find these stories of hidden engineering challenges fascinating, consider following for more deep dives into the forensics of our world. What do you think is the most important trait for an engineer, innovation or caution? Let me know in the comments.